Hello, my name is Emma Topolcsik. I am a second-year master's student at San Diego State University studying computational science. I do my research in the aerospace engineering department under Dr. Pablo Machuca, and today I will be talking about my project on an efficient optical navigation model for Monte-Carlo feasibility analysis, the limits of horizon-based cislunar autonomy. As an introduction, in recent years, missions in Earth-Moon or cislunar space have increased significantly. And optical navigation, also known as OpNav, is growing as an effective solution for navigation. Lots of methods have been investigated and implemented, such as previous work that investigated the performance of a novel horizon-based position estimation algorithm. And horizon-based just means that they're images of the moon that were taken, and by using the illuminated limb or the illuminated side of the moon to estimate the relative position of the spacecraft. And four discretized parameters determined the measurement accuracy, as shown in Figure 1, and its distance or range direction defined by two angles, and the time, which defines the illuminated horizon. And further work shown in Figure 2 identified error patterns and continuity across time. So this image just shows that the error patterns evolve along time and they repeat every synodic period. It's approximately 29 days. And furthermore, the error means are non-zero, which means that there is bias in these measurements. So it would be very interesting to explore the implications of these error patterns in this OpNav method. The biggest struggle is that obtaining high-fidelity OpNav measurements is computationally expensive. So this project builds off of the previous work to present an approach to efficiently assess OpNav performance and limits in cislunar space by four things. First, the 4D interpolation of the pre-computed data in the previous work, which is more efficient and maintains the fidelity of the measurements. And it's very helpful for the next step, which is incorporating these pre-computed measurements into a navigation filter with Monte Carlo simulations. And there's two filters that are explored, which is an extended Kalman filter, assuming no bias, and a separate bias filter. Third would be writing the simulation model in multiple programming languages, and we explore MATLAB and C++, and also to identify model simplifications that can maintain the complexity of the error patterns. And this can be essential for future lunar missions utilizing OpNav. So the simulation framework begins with the interpolation model that is developed for OpNav measurement data from the previous work, and this is done using linear interpolation. And this way, we can estimate the measurements at any point in cislunar space. There are two Kalman filters that are implemented as stated before. So first is a bias-free extended Kalman filter, and then an extended Kalman filter with a separate bias filter. The dynamics will follow the circular restricted three-body problem as shown here on the right. And this just means that orbits in cislunar space are influenced by the Earth and the Moon's gravity, so they both must be taken into account in the dynamics. So the flow chart here shows the extended Kalman filter that includes separate bias filtering. The highlighted pink box here is the bias-free extended Kalman filter. And what happens is that when the gain is computed, this gets incorporated into a concurrent filter that then estimates the bias. Once both are updated, they're combined at the end to get the state estimate with the bias. And the initial bias covariance comes from a reduced resolution version of the available OpNav data from the previous work obtained through interpolation, but that just means that the truth is the original OpNav data at those discretized points as discussed earlier. And some quick preliminary results. The results on the left show the bias-free results of a family of distant retrograde orbits, which are lunar orbits. And the point of this plot is to show that the navigation accuracies are in between 1 and 50 kilometers, which shows promise for future missions. And the image on the right shows the bias filter, the results from this. And the bias is currently modeled as white noise to understand the behavior of the separate bias filter. So some more refined results will be included at the ACSESS event on March 21st. And if you're interested, please come by my poster and ask some questions. Thank you very much.